اثبتي النفاس Okay, welcome to the week 7 live interactive session of NOC24 EE-28 signals and systems. The course instructors are Professor Hitesh Rimali and Professor Kushal Kesha. These are the prerequisites for this session, which include the last week's lectures that covered the following topics, namely Laplace transform and its inverse, rows and zeros, vision of convergence, ROC, Laplace analysis of LDI systems and RLC circuits. I hope you all would have gone through them and would have then attempted the assignment 7 before watching this session. Okay, let's recap briefly and then we'll move on to the problem section. Firstly, in this week we learned about Laplace transform, right? You can think of Laplace transform as a tool that reduces many difficult problems to simpler problems, right? For instance, under certain conditions, it allows to convert partial differential equations into ordinary differential equations. And likewise, under certain conditions, it allows us to convert ordinary differential equations into algebraic equations. And it finds wide use cases in the control theory. And we can think of this Laplace transform as a generalized Fourier transform. We have seen earlier that we can represent signals via their Fourier transform, provided they follow the Dirichlet's criteria. So if the signal follows the Dirichlet's criteria, then for that signal, we can write its corresponding Fourier transform x of omega, which as per definition is given by this, right? This is what we know so far. So let's develop a motivation for the Laplace transform. What about this unit step function, right? You remember this Fourier transform of u of t, it wasn't that straightforward, right? Why? Because Dirichlet's conditions, they are sufficient, but they are not necessary conditions. Even though it wasn't meeting the Dirichlet's conditions, but Fourier transform did exist, but uh, we needed to perform some mathematical jugglery to compute that Fourier transform. Right. In fact, I'm not sure. Yeah, I've mentioned it here. In week 3, we did compute Fourier transform of U of t in a different fashion, right? And if you don't remember that, you can refer to this link and you'll be redirected at that exact timestamp where we discussed uh, how we computed Fourier transform of U of t. The summary of that recipe was as follows. We multiplied U of t by this exponential decay factor e to the power minus 80 such that the resulting signal is absolutely integral. Okay. And then we took the Fourier transform of this signal. And since this is absolutely integrable, it meets Dirichlet's conditions and I can use this definition, right? So I can use that definition for this signal. I'll get some, say, u of omega corresponding to that, right? And then I'll take the limit a tends to 0 in that u of omega. And that gave me the desired answer. Why? Because in the limit a tends to 0, this signal is u of t, right? Because exponential of minus at goes to 1 as a tends to 0. So this particular recipe is actually a motivation. It will serve as a motivation for going towards Laplace transform, right? Because this kind of problem that we faced for u of t, uh, that is to compute the Fourier transform of this signal, we might face such problems for many functions, right, that are not well behaved. So what we'll do is we'll multiply those functions by exponential of minus sigma t, right? So that uh, as t tends to infinity, this f of t times exponential of minus sigma t tends to 0, right? In other words, this becomes absolutely integrable. But you'll notice that the above equation, it can still blow up as t tends to minus infinity, right? Because sorry, this factor would blow up as t tends to minus infinity. So, uh, just a second. Okay, for a while you'll ignore this part. Okay, actually this was for the unilateral Laplace transform, but ignore this. So as t tends to infinity, this f of t times exponential of minus sigma t tends to 0. Okay, now f of t times exponential of minus sigma t. I'll denote that by this capital F of t. And then we take the Fourier transform of this capital F of t instead of this. Okay, and this Fourier transform of capital F of t is by definition the Laplace transform of f of t, right? So one can see where the motivation for going towards Laplace transform comes from. So let's do the maths. Laplace transform of f of t we defined in previous slide by Fourier transform of capital F of t, where this capital F of t is small f of t times exponential of minus sigma t. Now, Laplace transform of the small f of t by definition is the Fourier transform of capital F of t. So I'll write minus infinity to infinity this f of t exponential of minus j omega t dt. This is by definition the Fourier transform of capital F of t. Right. Then I'll replace this capital F of t by this small f of t exponential of minus sigma t, because f of capital F of t is equal to that. Then I'll club these exponentials together. I'll get exponential of minus sigma plus j omega t dt. This sigma plus j omega, I'll then denote this by the Laplace variable s, such that s is sigma plus j omega t. Note when Note the differential of s is j times differential of omega, right? So yeah, what about its inverse? This capital F of t is 1 over 2 pi minus infinity to plus infinity f of omega exponential of j omega t d omega. Okay, so I'll multiply exponential of positive sigma t on both sides. Why? Because I'll get small f of t by that, right? This is this f of t is this f of t and capital F of omega are Fourier transform pairs. But I'm interested in getting a formula for this small f of t. So I'll try to express this integral involving this small f of t. I can easily see from this equation that when I multiply this Okay, do one thing, multiply this equation on both sides by exponential of positive sigma t. What do we get? Exponential of sigma t is f of t, right? Sorry, exponential of sigma t, f of t, that is this f of t. So this is f of t. And likewise, we need to multiply this exponential of sigma t on the right hand side as well, right? And then again, we'll club these two exponentials together. This f of omega will write as f of s, and we will replace this differential of omega by ds by j from this equation. And then this would be our, so this is our bilateral Laplace transform, and this is the inverse transform of that bilateral Laplace transform. Okay, so let's summarize what we derived. So Laplace transform of f of t is capital F of s, and this is the definition. Remember, this is how we define bilateral Laplace transform. A unilateral or one-sided Laplace transform also exists, and there this lower limit is different, right? So in nutshell, you can think of it as a weighted Fourier transform. And this integral may diverge for some values of s, right? And so defining this region of convergence is important. We'll take some examples on that. So the set of all the complex numbers s for which the above integral will converge, that set would be the region of convergence, ROC, of this Laplace transform f of t, right? Okay, this is the first example. So I'll take two examples to highlight why ROC would be important. So first example is this x of t is given by exponential of minus at u of t, right? And what would be x of j omega? X of j omega would be exponential minus infinity to plus infinity, exponential of minus at, this signal, exponential of minus j omega t dt. I've used Fourier transform definition over here, right? We'll also see in this example how Fourier transform and Laplace transform compare to each other. So since we have u of t in this integral, so I'll change the limit to 0 to plus infinity, right? So I'll be left with exponential of minus t, exponential of minus j omega t dt, and integral limits are from 0 to plus infinity. Okay, now this exponential can be clubbed as exponential of minus a plus j omega t, right? And what is the integral of that? The integral of this exponential is that it has been shown here, right? And the limits are from 0 to infinity. So when this t is infinity, this term goes to 0, and then we are left with this minus times minus 1 by a plus j omega. And when t tends to 0, this exponential is 1, right? So minus minus is plus, and I'm left with this 1 by a plus j omega. Notice a is greater than 0, right? Now Laplace transform x of s, that by definition is exponential minus infinity to plus infinity. This is the signal itself, this part. So I've used signal. And then we have this factor exponential of minus st, right? Dt. This is how we defined Laplace transform. So then again, since we have u of t, I'll change this lower limit to 0. Okay, and what would be my exponential if I club these? Exponential would be exponential minus a plus, yeah, minus a plus s t, right? This would be the exponential. And the integral from 0 to plus infinity dt, that would result in this OQ degree, right? Now we'll take the limits. When t is infinity, this whole term goes to 0. Okay, and then I have, and then when t tends to 0, this exponential goes to 1, right? So I have following. Right, and this term is 0. So I'll be left with minus minus is plus, 1 by s plus a. Exponential of 0 is 1. So I'll be only left with 1 by s plus a. And notice that this sigma is greater than minus a, right? Only then would this integral converge. So the real part of s should be greater than minus a, right? For else this particular term, let me show it. Otherwise, this particular term would be such that when t tends to infinity, this would blow up. For this to not blow up, this particular condition should hold true. Okay, so the Laplace transform would only converge for real part of s being greater than minus a. And since s is sigma plus j omega, I can write that real part of s is sigma. So sigma should be greater than minus a. Now, if a is negative, okay, or 0, the Laplace transform would still exist, but the Fourier transform does not. Can you see that? Right, because this x of j omega would only converge for a greater than 0, right? Because if a is less than 0, this particular signal would be an exponentially growing signal, and that won't converge as t tends to infinity, and hence that won't be absolutely integrable. So the Fourier transform does not exist, but this Laplace transform would still exist. So we don't have any condition over a, right, in this exponential in Laplace transform, as was the case with this Fourier transform. So a word of caution, it might seem tempting that we can compute the Fourier transform of x of t from its Laplace transform by setting x equal to j omega, right? Because if you see in this example, what is my Laplace transform? 1 by s plus a. It, we might be tempted that maybe if I use s equal to j omega for the results of Laplace transform, I might get the corresponding results for the Fourier transform. But that is not the case. Why? Because that is not valid in general. Why? Because if the set S is in the ROC of x of s, if that is not the case, then this won't hold good. So this is valid if and only if this set, right? The values of s, if they lie in the ROC of X of S. Only then can you use this particular thing. Okay. So with that, let's move on to the example. So we saw in this example, what did we saw? We saw that we got Laplace transform 1 by S plus A corresponding to some signal. And there was some ROC, right? The point of these two, the next example is such that we'll again get the same Laplace transform, but we'll have a different ROC. And likewise, we'll have a different signal to which it corresponds. So for example, if the sector of t is minus exponential minus at u of minus t, okay, what would be the Laplace transform in this case? First, let's write the signal. This minus was here and the rest part is here. Since this is u of minus t, this plus infinity upper limit goes to 0, right? Because u of minus t is this. That's why. So yeah, u of minus t I've already taken care of. And then I have this exponential of minus st dt, this part. Again, if I'll club these two exponentials, I'll have exponential minus a plus s t, right? Integral is from minus infinity to 0 dt. Okay. If I integrate this particular exponential, I'll be left with this, right? What I've done in this step is I've taken care of this minus sign by swapping the limits, right? Wait, have I swapped the limits? Yeah, I have absorbed this negative sign, right? There was supposed to be this minus sign here and a minus sign here. I multiplied those two minus signs and that's why there is no minus sign overall. So the limits of this would be from minus infinity to 0, right? Okay, so 1 by s plus a. Let's take that common. I'm left with exponential of minus plus a times t. When we'll take the upper limit first. So t, when t is 0, this whole argument is 0, minus exponential of when this t is infinity. Sorry, when this t goes to minus infinity, this, okay, when t goes to minus infinity, this term should go to 0 in this limit, right? When real part of s plus a is less than 0, then as t tends to minus infinity, this should go to 0, right? So I'll be left with 1 by s plus a. Notice in this case, I have following ROC. Here, the ROC was R of s, the real part of s is greater than minus a, or sigma is greater than minus a. Here we have sigma is less than minus a, R of s is minus a. Otherwise, the Laplace transform that we computed was exactly the same, right? And since the ROC is different, I have two different signals in the time term. So right, we'll today explore this particular part in the sample problems where we'll be given some Laplace transform and an associated ROC, suppose ROC1, and then we'll have to compute the inverse Laplace transform, right? And then we'll have some different ROC corresponding to that same uh, S domain function, and we'll have a different time domain signal. The reason is uh, the Laplace transform of a signal, both the algebraic expression and range of values of S, the ROC, right? They both somewhat characterize this Laplace transform. So yeah, we noted that the Laplace transform is identical for both the signals. This is the summary, right? Exponential of minus at u of t, the Laplace transform of that is 1 by s plus a, and the region of convergence is real part of s is greater than minus a. Likewise, for this particular signal, we had the same Laplace, the algebraic expression in Laplace transform as domain, but the ROC was different. So conversely, what I can do is I can give you this algebraic expression and I'll say you this is the ROC. Then the inverse Laplace transform should be this, right? Not this. Likewise, I'll give you the same algebraic expression and I'll say you that ROC is this. In that case, this should be the expected answer, right, from your side. I hope the point was conveyed. Okay, these examples also illustrate the fact that in specifying the Laplace transform for signal, both the algebraic expression and the range of values of s for which this expression is valid, ROC are required, right? Not only the algebraic expression is required, but also its corresponding ROC is required, right? Only then would we be able to uniquely compute the inverse for your inverse Laplace transform. Okay, then we have some properties of region of convergence. We'll only state them here. If you are interested in proof, probably might have been covered in the lectures, last week's lectures. I'm not sure. If not, you can refer to the recommended book in this course, right? Oppenheim. There, these properties are discussed in more depth. And if you are eager to learn, you can go over to there. So ROC of X of S consists of strips that are parallel to j omega axis in this plane. Right. Okay. For the rational Laplace transform, the ROC does not contain any pole. Okay, remember this fact that ROC won't contain any pole. And x of t is, if x of t is of finite duration and it is absolutely integrable, then the ROC is the entire S plane. Right? These are some results which can keep in your mind, right? It might help you with some questions. For example, if I had any x of t, right? What does this property state? If I had any x of t and it was of finite duration, if it was absolutely integrable, then ROC is entire plane, right? Property 4 is if x of t is a right-handed side, a right-handed signal, and if this line R of s is equals to sigma naught is in the ROC, then all the values of s for which R of s is greater than sigma naught will also be in its ROC. Right. Likewise, we have property 5, which is kind of a dual of this property 4. Then property 6 is if x of t is a two-sided signal. Notice from property 4 and property 5, if I have a right-handed signal, its ROC would also, extend towards the right-hand side. Right? R of s greater than sigma naught. What does that mean? I have some sigma naught and ROC is greater than the sigma naught. Right? Likewise, if I have a left-sided signal that extends to the left side, then the ROC would also be left-sided in the sense if I have this sigma naught, the ROC would be this. Right? So property 6 states that if x of t is a two-sided signal and if this line is in the ROC, right? Real part of s being sigma naught that lies in the ROC, then the ROC would consist of strip in the S plane that includes the line R of s equals to sigma naught. Okay. Then we have property 7. If the Laplace transform of x of t is rational, then its ROC is bounded by poles or extends to infinity. In addition, no poles of x of s are contained in the ROC. Okay, so actually we'll see this one in the question also today. We'll be given a rational function x of s, Laplace transform of x of t, uh, then its ROC would either be bounded by the poles or it would extend to infinity, right? And in no scenario would poles be contained in the ROC. Okay, remember this part. If the Laplace transform, then the property if the Laplace transform x of s of x of t is rational, then if x of t is right or left side, then the ROC is the region in the S plane to the right or left of the right or leftmost pole. Okay, now we can read the sentences. X of t is a right-sided signal, right? For a moment, forget this left part. X of t is right-sided, then the ROC is the region in the S plane to the right of the rightmost pole. There would be many poles, right? The rightmost pole, the ROC would be right of the rightmost pole. Something like this scenario, if it had two poles. On the other hand, suppose this rational function, this rational expression x of s had many poles and its time domain signal x of t was left-sided. Suppose it had these many poles, then the ROC would be, if x of t is left-sided, then it would be ROC would be left to the leftmost pole. Something this, right? Because this is the leftmost pole. Okay, remember this. We'll revisit this if needed. Then we have some properties of Laplace transform as we had for the Fourier transform, right? It's quite natural to expect that Laplace transform would have some similar properties. For example, linearity. This one follows readily from the linearity property of integral, right? So if x1 of t has a Laplace transform x1 of s, suppose the region of convergence R1. Whenever we are given Laplace transform pairs, uh, do try to have in your mind what is the ROC corresponding to that. For example, here the Laplace transform pairs x1 of t, x1 of s have R1, right? You'll be given ROC as R2 for this, and then suppose you are asked to compute this one, right? A linear combination of x1 and x2. Then the Laplace transform would be given by a times x1 of s plus b times x2 of s, the same thing that we did in Fourier transform, but the ROC would be the intersection of these two. Okay, what do I mean by that? Wait, I'll use this. Suppose this was R1, okay, and this one was R2. This goes to infinity. This goes to infinity. Then this R1 intersection R2 would be this common one, right? And this green part would be the ROC for AX1S plus BX2 of S, right? Because R1 intersection not is given like this green part in this case. Yeah, let's move on to the next property. Then we have time shifting property. If x of t, okay, a word of caution, these properties that I'll show will be for this bilateral Laplace transform, and we'll see where do these properties differ for the unilateral Laplace transform. I hope you remember that. For the unilateral Laplace transform, the lower limit is 0, and for the bilateral Laplace transform, lower limit is 1 to infinity. Okay, we'll see where do these properties differ for these two transforms. For the time shifting, we have x of t minus t naught. Its Laplace transform is e to the power minus s t naught x of s, where x of s is the Laplace transform of x of t. The ROC is unchanged. Okay, ROC remains R, whatever the ROC was for this. Now shifting in the S domain. Okay, x of s minus s naught would have this e to the power s naught tx of t as the inverse Laplace transform, and the ROC would be this. The R, the existing one, plus this s naught. Okay, real part of s. Then, yeah, then we have time scaling. Uh, the result is familiar to the one we saw in Fourier transform. Notice ROC changes in time scaling. Okay, the new ROC would be R1, and that would be given by A times R. So in a way, the region of convergence also scales, right? Uh, Apart from this Laplace transform. Then we have conjugation. Uh, x of t, x of s being the Laplace transform pairs with ROC R. If I have a conjugated signal x star of t, its Laplace transform would be x star of s naught. Okay, the ROC remains same. Then we have convolution property. This you can readily read. Yeah, notice if ROC here was R1 and ROC here was R2, and if I take convolution of the two signals in S domain, they would be multiplied, but ROC would be the intersection of the two, right? R1 intersection R2. Now differentiation in time domain. This particular part, this is valid for bilateral Laplace transform. Okay, and quite often you will be using different. So let me first discuss this. If I differentiate the signal in the time domain, in Laplace domain, I have this, right? Sx of s. For proofs, you can refer to the book or watch the week's lectures. But if you have any doubt, you can let me know in the chats. So ROC is unchanged. Okay, this part is for bilateral Laplace transform. Okay, now had I considered unilateral Laplace transform in which the lower limit was 0, right? Then this property is differed. For property up till 6th, till here, whatever properties I showed you for the bilateral Laplace transform, they were valid for unilateral as well. Here it differs, right? For the differentiation in time domain. How does it differ? If I differentiate the signal in the time domain and compute its unilateral Laplace transform, then this is the result. Okay, as x of s, where this x of s is unilateral Laplace transform of x of t, minus x of 0 minus. Okay, this x is the time domain. X of t and t equal to 0 minus. Okay, that was something that you should have known. Then we have differentiation in the S domain, a dual property of that. For this property, yeah, I don't think unilateral and bilateral differ for this one. So if I differentiate in the S domain, in the time domain, I need to multiply this by minus t. I guess in Fourier transform it was minus jt. Here it's multiplication by minus t. Okay. ROC remains unchanged for both this and this. Then we have integration in the time domain. For the integration in the time domain, This particular expression has a Fourier transform x of s by s. Okay, we are dividing this by s. Here we were multiplying this by s. Here ROC would be this R intersection real part of s greater than 0. Right, whatever is the intersection of these two ROCs. One ROC among them is this real part of s is greater than 0. Okay. Other one is whatever was the ROC for this Laplace transform. Then we have the initial and final value theorems. This x of 0 plus is equal to limit s tends to infinity as x of s, the initial value theorem. This one. This is valid provided this x of t is equal to 0 for t less than 0. Okay, so it is 0 for t less than 0. It only exists for t equal to or greater than 0. And x of t should not contain any impulses or higher order singularities at t equal to 0. Right, these are the conditions under which this initial value theorem is valid, and you can use this result for many problems. Likewise, we have a final value theorem which states that limit t tends to infinity x of t is limit s tends to 0 s x of s. Okay, again this is valid provided x of t is equals to 0 for t less than 0, right? This part is same. And in addition, we have one more I would say a restriction that x of t has a finite limit as t tends to infinity. Okay, so if this condition is followed, then you can use this final value theorem, wherein you are computing the limit t tends to infinity of x of t by using its Laplace transform using this. So this was initial value theorem. This is final value theorem. With that, we'll move on to the first sample problem. For this h of s transfer function, you need to determine how many different LTI systems can have the same transfer function. Remember, we discussed that a same algebraic expression of Laplace transform can have different inverses, right? Corresponding to different ROCs. So basically, this question is, in other words, asking you to find how many different ROCs do you have, right? Try this out and let me know. I hope I'm audible. I'll wait for 1 minute and then solve it myself. Please let me know if you do it before. You can let me know the answer in the chat or by unmuting yourself. Yeah, let's start. So your h of s is given by this one. So what are your poles? You'll have two poles, right? Pole one, where would be the pole one? Pole one would be at setting this to 0, right? When this is 0, I'll get -1 -2j. So pole would be at -1 -2j. Likewise, I'll have pole 2. Where would be that? Where would be the pole 2? Would be at -1 +2j. Okay. Then let's draw a pole 0 plot. So this is 2j, this is just a second. Right. So now where are these poles located? They are located at -1 -2j, -1 +2j. Somewhere around here. Somewhere around. Right, this is our pole 2. Now where is pole 1 located? Pole 1 is located here, right? If you are interested. Okay. So this is a pole 0 plot. The given transfer function did not add any zeros, right? So I only located the poles. This is my pole 0 plot. This was the sigma real part of S and this is geometry. Okay, once we have that, then we need to comment on the ROCs. What kind of ROCs could we? We learned that ROC cannot contain poles, right? And ROC, let me in fact navigate to here to show. See, we learned these two things, right? At ROC of X of S, it consists of strips parallel to j omega axis in the plane, right? So it is parallel to the j omega axis in the plane. And we also learned that no poles are contained in the ROC. So we are left with two choices, right? First choice is, let me draw first a strip. First one is this, where ROC is to the right of these poles throughout this entire plane. My other option is that ROC is here, right? To the left of these poles, right? I can only have these two scenarios. So I can have two ROCs, right? What are my possible ROCs? Number one would be that my real part of S, right? Real part of s is greater than -1. Real part of s is less than -1. Those would be the two ROC cases, right? So real part of the other one would be the real part of s is less than -1. Right. Let me in fact draw this as well. Right, this is my ROC. Likewise, wait. Okay, me. Right. This is my ROC1. This is my ROC2. Right. So this one extends all the way to infinity. Likewise, this one extends all the way to infinity. These are my two ROCs. So how many different LTI systems can I have? Right. I was given this h of s, right? How many different h of t can I have? Impulse responses of the LTI systems. Two, right? Corresponding to these two ROCs. Right. I have two different. Therefore, and we having two different these LTI systems. And I have same transfer function. Given by this particular. Okay, so the correct answer is 2. Let's move on to the second question. Okay, now we'll proceed a little faster. Now this is your h of s, right? This is actually the same transfer function from the question one, and you need to determine the inverse Laplace transform of that equation. What would be the inverse Laplace transform? So I should start myself as well. So we have been given h of s is this. I can in fact HFS, can write HFS as S plus 1 S plus 1 minus 2J. Right. The denominator is of the form A plus B into A minus B, right? So A square minus B square. What does A square minus B square give? S plus 1 square minus 2J square. Right. So then this H of S would be divided by S plus 1 square plus 4. Right. So let me start this from that technique. So this is what I have obtained. H of S is 1 whole divided by S plus 1 square plus 4. I can multiply and divide on both sides by 2. Why? Because I can first write this as S plus 1 square plus 2 square. Right? And this looks familiar to me. Right? Because I know that sine of 80, right? Sine of 80, the Laplace transform of sine of 80 u of t. What is the Laplace transform of that? The Laplace transform is given by a whole divided by s square plus a square. And the ROC is real part of s is greater than 0. Okay. So what would be the inverse Laplace transform of this? This one, right? But first I need to express my h of s in this form. Here a is in the numerator, right? So I need a 2 in the numerator. That is the reason why I'll do following. I'll write h of s is 2 whole divided by s plus 1 square plus 2 square. Right? And then for the ROC, real part of s is greater than 0, what I can write h of t as, and write h of t as, wait, sorry, I missed a factor. Right, my h of s was this. So if I need 2 in the numerator, I need to divide by 2 as well. So this is half times this one would have been this sine of 80 u of t had this been s square. But since this is in this expression, I have s plus 1 instead of s. Which property should I use? This is basically shifting in the s domain, right? And for the shifting in the s domain, right? In my case, this s naught is minus 1, such that this x of s minus s naught is x of s plus 1, right? So my s naught is minus 1. So I would have exponential of minus t factor in the time domain. So I'll use that. I'll have exponential of minus t, and then I can use the result as it is. Sine of, here this a was 2, so I'll use 2 sine of 2t u of t, right? Right, this is my h of t, and also notice I use this property, right? So the ROC would be ROC R in this case plus this real part of S0, right? So here ROC was real part of S was greater than 0. So I'll have this plus real part of S0, and the real part of S0 is S0 is minus 1. Okay, let me know if you have any doubts. With that, I guess we'll move on to the third question. Yeah. So this is the third question. You need to determine inverse Laplace transform of this equation 2. And notice you have been given ROC, right? So you can uniquely compute the inverse Fourier transform. I guess I'll start doing it since we are short of time. Nobody among you is responding, so let's start doing it. So question number 3 is, surface is 1 by s squared plus 5s plus 6, right? This is h of s. I'll first factorize it. Okay, I'll factorize it, obtain this, right? Simple factorization. Then what I'll do is uh, I'll use partial fractions. I mean, I have options here. Either I can use partial fractions because that method would be valid in general. Using partial fractions, we can then write this 1 by s plus 2 s plus 3 as a by s plus 2 plus b by s plus 3. We already discussed, I guess, in week 5 or week 6, what are the partial fraction forms and what are, I mean, we recapped that to get an overview. So you can refer to those slides as well if you need help. Refer to the supplementary material in those slides. So here, if you'll solve this, you'll get a equal to 1, b equal to minus 1. Okay. And as we also saw in many previous questions, we can alternatively do the following. You can write this 1 by s plus 2 s plus 3 as s plus 3 times s plus 2 whole divided by, right, numerator is anyway 1, so I can do this. Then this is 1 by s plus 2 minus 1 by s plus 3. Notice we got the same answer doing this and this. B is minus 1. Right. Now what we'll do is we have h of s as 1 by s plus 2 minus 1 by s plus 3. So I'll use inverse Fourier transform and use the linearity property. Right. I can compute individual uh, ways. Inverse Laplace transform. Sorry. So now, but answer to this depends upon my ROC, right? Here I have been given that ROC is less than minus 3. So my ROC, real part of is this is my ROC. Okay. Real part of s is less than minus 3. Let me in fact draw this ROC. The next 2, 3 questions are basically the same transfer functions with different ROCs, right? So pay attention. This is 0, this is sigma, this is j omega. Right, this is minus 2, minus 3. Right? 2 poles, right? My transfer function had 2 poles, one at minus 2 and other one at minus 3. The ROC, real part of s is less than minus 3. This, let me draw that. Wait, but I'll first copy this because I'll be needing this. Okay. Up to this point. Extends then all the way to infinity. Yeah, this is the real part of s being less than right. Now pay attention to this one. Here the pole is minus 2, right? And real part being less than this. Okay, I remember we had discussed 2 examples at the start of the lecture. We have similar, uh, right? We had a 1 by s plus 2 and here it was 1 by s plus a. Real part of s being greater than minus a, right? If this is the scenario, then x of t is given by this function, right? And when I have the same function and my real part of s is less than minus a, I have this x of t, right? I'll use this particular fact. In fact, let me copy this for your reference. Right. What about 1 by s plus 2? Will 1 by s plus 2 be this case? Why? Because if real part of s is less than minus 3, then I can write that real part of s is also less than minus 2. Right? So for that one, I can readily use this result. In fact, for this, both the poles, pole minus 2 and pole minus 3, for both these terms, will fall under this case. Right? So what should be my this h of t? My h of t should be minus exponential minus 2t, right? U of t, sorry, u of minus t, right? Plus, I have plus, sorry, I mean, see, I had one minus, right? And then minus is plus, that's why I'm clubbing both minus signs. Exponential of minus 3t, u of minus t. Hope you all agree that this would be the answer corresponding to the ROC. Real part of s is less than minus 10. Now let's have another question in which we have the same transfer function. The only thing is that ROC now is greater than minus 2, right? ROC now is greater than minus 2. So this is, sorry. So this is my minus 2. ROC is greater than all the way to. So what will happen in that case? For this pole, the result is clear, right? It will fall under this case, right? My A is 2, so real part of this is greater than minus 2. For this particular term, notice for this transfer function, I can also reach here, right? I mean, the steps will be same and I'll skip them. But what about this pole? For this, also, wait. Sorry, sorry. This was minus 3. This was minus 2. And nobody objected to this. Should have pointed out if I swap the numbers. Anyway, the result would still be the same for this question, right? Real part of s being less than minus 3. For minus 2 pole, it would still be less than this, right? In the left, to the left of this pole. So I'll still have this result hold good. But what about the case when I have my ROC, which is greater than minus 2? Okay, now my ROC is this. Real part of S is this region. Now for this case, this particular term has a pole minus 2, right? This term. I'll first write this result as well. The bicycle. It's not necessary convergence. So I have SH of S given by 1 by S plus 2 minus 1 by S plus 3, right? And also this particular. Now, this one it's clear, right? I'll be using this result. What about this? S plus 3 1 for this pole. For that one, would you agree that I need to use this result? I mean, for 1 by S plus 2 and 1 by S plus 3. In this scenario, real part of S is greater than minus 2. So it's also greater than minus 3. So in both these cases, I'll be using this result, right? This is pretty straightforward. I guess we should not spend time on this one. So my h of t, what is my h of t? That would be exponential minus 2t u of t plus I guess I should have a minus sign, right? Yeah. So which option is correct? Will we have a plus sign? We shouldn't, right? Just let me check this. Hold on. Anyways, this would be h of t, right? I'll check if there is a sign mismatch for this. Probably it should be minus, right? I'll check this. You can let me know in the comments if there was a mistake from my end or in the question. Now, what about this scenario? You need to determine the inverse Laplace transform. Again, the transfer function is same. Only thing that has changed is the ROC now, right? The ROC is from -3 to -2. Right, let me just copy this again. Let's try making a new one with tick listing. So now our ROC is between this -3 and -2. Okay, I'll shade that part. My ROC is this part. Okay, again, bring this up for your convenience. Was my h of s. H of s would be same, right? Because I can again convert that h of s that was asked in question 3 to this one, right? So these three questions were same. Only thing was at three different ROCs. This one is actually bounded between poles. The ROC that is bounded between poles. So my again h of s would be 1 minus plus 2 minus s plus 3, right? Now, yeah. Now for this one, pole of interest is -2. For this one, the ROC is to the left of this pole, right? Since it is to the left of this pole, which result should I use? I should use this result. Right? I hope you all would agree. So while writing h of t, I'll use this minus exponential minus 2t u of minus t. Now for this one, the pole of interest is real part of s is equal to -3. Right, this is sigma and this is geometric axis. This was 0. So for this pole, the ROC is to the right of this pole. Right, that corresponds to this one. So I'll use this result. What would be it? Minus, since I already have this. I'll be using this result now, right? Because ROC is to the right of this pole. Exponential minus 3t u of t, right? So which answer is correct? I guess there was some issue with the sign for question number 4. But for this question number 5, the correct answer should be the first one, right? Minus exponential of minus 2t of minus t, and then this minus exponential minus 3t. Right? Do one thing for question number 4. Since probably there is something wrong with the sign, so consider this sign being plus, this sign with okay. Okay, I have changed this sign, and the question 4, the answer that we got was this one. So correct answer should be this one. Okay, let me know if you have any query. So then we have question number 6. Let's quickly start that one. We'll start question number 6 now. So if K represents the DC gain, then the inverse Laplace transform of figure 1. Okay, this is the figure. DC gain is K. ROC is also provided. We need to comment on the form, the inverse Laplace transform, what will be its form. Notice we have K in the options as well. So what are the poles of from this pole 0 plot? The poles are, I have one pole at s equals to -2, right? I have pole at s equals to, what is this one? This is minus 0.5 minus j, right? Minus 0.5 minus j. Similarly, pole 3 is minus 0.5. Sorry, this one is plus 1, right? Sorry. Okay, now it's fine. Minus 0.5. Okay, pole 2 was this one, right? Pole 2 was this one. Pole 3 is minus 0.5 minus j. Okay, this one. Now, if I have these 3 poles, what would be the form of my this S domain? Right, my this h of s. What should be the form of that? H of s would take following form. I have a pole at -2, so s plus 2 term corresponding to that. I have poles at these 2 points, right? So I have this s plus 0.5 minus j and s plus 0.5. Yes, I need s plus 0.5 plus j, right? And since I have a DC gain k given in the question, I'll use that. That will remain unchanged, right? Be it the inverse Laplace transform or the S domain. K would remain unchanged since can treat it as a constant. Okay. Now I'm interested in computing the inverse Fourier transform of this h of s. And what is the ROC? My ROC is this real part of s, the real part of s that is greater than minus 0.5. Okay, so let's proceed. And this question I'll speed up. My h of s is a whole divided by s plus 2, right? S plus 0.5 minus j and plus j. If I take this as a and this as b, so this is a minus b, a plus b. That is a square minus b square. That is what I'll use. So this would be s plus 0.5 square, right? A square minus j square, isn't it? My k is the DC gain that was given in the question. Now h of s is a whole divided by s plus 2. Now if we simplify this one and get s plus 0.5 whole square plus 1, right? J square is minus 1 and minus is plus. So h of s is, suppose this is my alpha equation, okay? Now h of s is a whole divided by 1. Simplification, you'll get this s plus 2 s square plus s plus 1.25. Okay. Now if you'll use partial fractions, what would you get? Using partial fractions, we can write this 1 by s plus 2 s square plus s plus 1.25 as this a by s plus 2. But since this is a quadratic expression of s, you'll write plus bs plus c. Write this form. S square plus s plus this 1.25 can be written as 5 by 4. So I'll go ahead and do that. After that, uh, when you'll take out an LCM, in the denominator you will have these two terms, and A will be multiplied to this, and BS plus C would be multiplied with this, right? So after simplification, this is what you would get. 1 is equal to A times, I'll show that this S plus 2 S squared plus S plus 1.25 A times S squared plus S plus 5 by 4 plus S plus C, right? S plus 2 whole divided by this, and whole divided by this, S plus 2 S squared plus S plus 1.25, right? Then I'll simplify it as follows. There's a stroke eraser and cancel denominator on both sides, right? I'll be left with this. Right. Let me further simplify this. I simplify it further, I'll get following. 1 is equal to A S square plus AS plus 5 by 4A plus BS square plus 2BS, right? Plus CS plus 2C. Now, if we'll put S equals to 0, right, now I to determine this A, B, and C, right? Because I'm interested in using this form and then proceed from there on. So what I'll do is I'll put S equals to 0. When I do that, which term would go to 0? S would cancel, this would cancel, this, this would cancel. I'll be left with this and this, right? So this is what I would get. I would get 1 that is equals to 5 by 4A plus 2C, right? Similarly, if I'll put S equals to minus 2, S equal to minus 2 would also simplify it. You can similarly put any value of S and form uh, linear equations, right? These are basically three variables. So you need three equations with three variables, or you can eliminate one and solve them. It's up to you. So if I put, let me use another page wide. At S equals to minus 2. Left hand side would again be S. Now, when S is minus 2, this S square would be 4. So I'll be having 4A, right? S is minus 2, so it would be minus 2A plus 5 by 4A would remain unchanged. BS square would be 4B. 2BS at S equals to minus 2 would be minus 4B plus CS would be minus 2C, right? Because S is minus 2. Right. In fact, you can now understand why we took S equal to minus 2. The motivation was to eliminate B and C. So this and this would go. And that is what we shall do. And we'll try to obtain what is A. Sorry, this was right because when S is minus 2, this would be minus 2A. So now I'm left with 1 that is equals to 4 minus 2A is 2A plus 5 by 4A. This would be A 2 plus 5 by 4. That is A. I guess this is 4 to the 8 plus 5 is 13 by 4. So a 13 by 4 factor. So 1 is equals to A times 13 by 4. A would be inverse of this, right? So A would be, we use 4 by 13. Okay. So that's how we compute A. Then we can use this particular equation to compute C. I'll encourage you to do that when you, or alternatively, we can do one thing. We can express the, okay, see, this is what we have. We simplify X, right? I'll club the coefficients of S square, S, and then a constant term, right? If I'll do that, we'll get following thing. 1 is equals to A plus B square plus, what are the coefficients of S? 2B and C, right? 2B plus C. A plus 2B plus C, sorry. A plus 2B plus C, S. And the constant terms are 5 by 4A plus 2C, right? Now this equation I already have, right? This constant term is 1. What about this and this? These two equations would give me A plus B is equals to 0. In fact, I should use a different. Why? Because coefficient of S square on the left hand side is 0. So that should be the case for right hand side as well, right? A plus B is equals to 0 and A plus 2B plus C is equals to 0, right? Now, what would this give me? A plus B equals to 0 would give me A is equals to minus B, right? So that's it. I computed B because I already know A is 4 by 13. So what should be B? B should be minus A. So minus 4 by 13. Now, what about C? I'll use that A equal to minus B in this one. That would, I'll use this. Okay. If I use this here, I'll get B plus C is equals to 0. Right. So B is minus C. Sorry, C is either way. C is minus B. So B was minus 4 by 13. So C is 4 by 13. Right. C is 4 over 13. Okay. So you have your A, B, and C. Right. Now, why did we need them? We needed them because we expressed using partial fractions our HFS into this form. So now we'll use A, B, and C. So our HFS, what is our HFS then? HFS would be K, right? See, its K was already there, a constant. I had computed partial fractions for this 1 by this thing. So K times this. K times my A is 4 by 13. S plus 2, right? Plus minus 4 by 13 times S plus 4 by 13, right? This is B and C. Denominator is S square plus S plus 5 by 4 and G. Now I'll do one thing. I'll take this 4 by 13 factor common throughout. I'll be left with following. H of S is equals to 4K by 13 1 by S plus 2 plus, okay, I'll write this term first. 4 by 13 has been taken out, so it would be 1 by S square plus S plus 5 by 4, right? Plus minus, now I'm concerned with this term, would be minus S whole divided by S square plus S plus 5 by 4. Now, remember this equation alpha? This was obtained from this one, right? I'll use this form again instead of this. So my H of S is 4K by 13 1 by S plus 2 plus 1 by S plus 0.5 squared plus 1, right? Use this one. Minus S whole divided by S plus 0.5 squared plus 1. Okay. Now the problem, okay. Remember that our ROC is was given in the question that ROC is real part of S is greater than 0.5. Sorry, minus 0.5, right? So this was right. So what is my ROC? My ROC is this part, whatever sigma is greater than 0.5. Now for If that is the case, as we saw in previous questions, I'll not I'll now write this expression for h of t. Would be h of t. H of t would be 4k by 13, right? Exponential of minus 2t, right? See, for this one, if real part of s is greater than minus 0.5, then real part of s is greater than minus 2 as well. So I can use the result that inverse Laplace transform is equal to e to the power minus 2t u of t. I'll take that u of t common throughout, right? What about this one? The Laplace transform would be given by inverse Laplace transform would be given by exponential minus 0.5t. Why? Because this is shifting in the s domain, right? And since for if this shift would not have been there, right? If this shift would not have been there, if this shift, then uh, the ROC was real part of s is greater than 0. Now, since this shift is there, then my ROC would be real part of s is greater than minus 0.5, and that is what has been given, right? So you can readily use this. Make sure you understand which result to use for which ROC. And then you have this s by s plus 0.5 square plus 1. This is cos, right? Exponential minus 0.5t. Why this exponential factor again? This we had this shift in s domain. So cos t. Right, h of t is done. Now, uh, what about this question? See, we already got this, right? We'll now use this for the, I guess, next one or two questions. This is basically the same question. Only thing that's different is your ROC is real part of S is less than minus 2. Okay, so I'll first, this is something that we already obtained, so we'll not waste time on this one again. And my ROC is real part of S. Real part of S is less than minus 2, right? That is what my ROC is. So I guess I'll copy this again. Right now my ROC is less than minus 2, right? So this is what my ROC is. So what should the answer be? Answer would be, we already discussed this many times in this session. So I'll just directly use it. Because the ROC is R of S is less than minus 2, this 1 by S plus 2, the inverse Laplace transform would be okay by 13 is anyway a constant. It would be minus exponential of minus 2t, right? And then there is this u of minus t as well. I'll take that common throughout, right? Because that would be the case for all these expressions. This, the next one is 1 by s plus 0.5 square plus 1. This would be minus, of this we had used a plus. Okay. Exponential of minus 0.5 t sine of t. Okay. And there is already a minus sign here, right? That's why minus would be plus, so it would be exponential of minus 0.5 t cos of t, and then there is u of minus t. Okay, so for earlier one, which option was correct? For this one, option B was correct, I guess, right? Let's check it. So in our question number 7, minus, I guess C part, right? Yeah, oh, this is fine. Now what about this one? A represents DC gain, then the inverse Laplace transform of the same figure with the ROC between these two, right? Now the ROC is between these two. This is where you have to search. For this case, you'll have following thing, right? This, for this pole, ROC is to the right of this pole, right? So you will use this result. Right? I'll directly write that, right? No point in showing that separate. 4k by 13 exponential of minus 2t u of t. Right? Because ROC is right to the right of this pole. And in fact, draw this on the same page so that you don't get confused. Right, your ROC is this one. Now, for this pole, ROC is to the right of this pole. That's why I used this one, right? U of t and a positive sign. And for the other case, okay, by 13. What about this case? For this, ROC is to the left of the pole corresponding to this, isn't it? Yeah, I mean, poles are this and this, and ROC is to the left of the poles. So I'll answer would be this. I'll directly write the answer. All would agree with me that the answer is minus exponential minus 0.5 t sine of t, right, plus exponential minus 0.5 t cos t. And then I'll have a u of minus t. I'll write it plus exponential minus 0.5 t cos t of minus t. Okay. So which option is correct? 4k by 13. And I guess the last one, right? The last one is correct. So with that, let's move on to the last question for today. By the way, I have kept the Laplace transform of sine and cos in the supplementary material. You can have a look at that. So you need to determine the transfer function in Laplace domain for the following equation, and you'll take initial conditions to be 0. What we will do is, let me quickly solve this one. So we'll be using unilateral Laplace transform for this one. Okay, and this unilateral Laplace transform, right? It's especially useful for analyzing the systems that are described by linear constant coefficient differential equations. Okay, which are having non-zero initial conditions, right? This unilateral Laplace transform finds use cases for such kind of problems. Okay, so in this case, we have anyway initial conditions as 0. So I'll be using following two properties of unilateral Laplace transform. The first one is, if I have following thing, right, my y of t in the Laplace S domain, this is y of s. If I take a derivative of this, right, dy dt of y of t in the Laplace domain, no answer would be the Laplace transform of this would be the s y of s minus s y of 0 by. Okay, s y of s minus y of 0. We already discussed that in property section. You can refer back to there as well. And similarly, if I have a second order derivative y of t, the unilateral Laplace transform of that would be s squared y of s minus s y of 0 minus y dash of 0. Okay, this is what I'll be using. And for the system in which is at 0 initial rest, right, in which the initial conditions are supposed to be taken as 0, then this y of 0 is equals to y of 0 minus is equal to 0, right? Because we are given that. So let me now take, this is the equation that is given, y double dash of t plus 5 times y dash of t plus 6 times y of t, that is equals to x dash of t plus 20 times x of t, right? This equation. Now I'll take the Laplace transform, the unilateral Laplace transform out. What I'll be left with, this is a double derivative, right? So I'll use this result. And since y of 0 and y dash of 0 are 0, because it is already given, So what I'll be left with is following: s square y of s, right? I have these terms, let me still write them. Minus s y of 0 minus y dash of 0 plus 5 s y of s. Again, there is a term, but that is 0 since initial conditions are 0. Right. What is this equal to? This is equal to s x of s minus x of 0. I hope I did not make a mistake. Yeah, now it's fine. Plus 20 x of s. Okay. Since I was supposed to consider initial conditions as 0, these gray terms would be 0. And what I'll be left with is following: s square y of s plus 5 times s y of s plus 6 y of s, that is equals to s x of s minus x of 0 plus 20 x of s. Okay, now this would give me y of s by x of s as s plus 20 all divided by s square plus 5s plus 6. Right. So this is the answer. So which option is correct? Option A. Right. That will end today's session. You can let me know in the comments or mail me if you have data. Thank you.